over to you, Barry, for an introduction.
Yeah. Okay. We good to go?
Yeah, good to go.
Okay. Good evening, everyone. Tonight we've got Peter Halman to give us a talk on two-stroke model engine design and development. Many of you will know Peter from his control line speed and performance engine developments, and also being the Ron Irvine's right-hand man in the manufacture of the wide range of Irvine engines. So with that, no further ado, over to you, Peter. Thank you very much.
Thank you, Barry. Well, good evening, everybody. I just thought I'd start off the presentation this evening with a little bit of background of myself and what I've been doing in order to get to where I am now. As Barry said, I've worked for Irvine Engines / Ripmax for quite a lot of time. It's the last 45 years since I started with Ron. And during that time, I've designed and developed all the Irvine range of engines except the Mark 140. Before I get into the technical stuff, some information about me and how I started an interest in model aircraft engines. Interest started in model aircraft engines goes back to 1959. I was 14 years old. Dad came out from Aden and he brought me an ED Hornet as a present. Now, I never flew the engine because it wasn't that wonderful, but I had a great deal of fun. I'm running it, learning how to operate small diesels, making a lot of smell. And it's amazing how the neighbors in those days were a lot more amenable than they are today, because nobody seemed to bother about the noise of this engine running in the back garden. I progressed through there for lots of other engines. I ended up with an ancient 2cc K engine, a Kestrel engine. Interesting. I wish I could find it and tell you a photograph of it, because it had the intake on the bottom of the crankcase instead of the top. It was not a tower of power, but it was great because it was the engine I used to make my first control line flights, and it just about staggered around the sky, which was perfect. I then got some PAW 249s, flew in combat models, eventually acquired an Oliver Tiger, which was a revelation in how engines should go. First glow motor was a Merco 35, followed by a Merco 61. I purchased these when I was RAF Halton during my apprenticeship, which ran from 62 to 65. Most influential moment for me, that was attending the 66 World Champs at Swindon and seeing the TWAs in operation. Oops, wrong screen. Just get that change over. That's me Mercos. I'm not quite used to running a slideshow and chattering, so you'll excuse me if I don't always get the slides up as I'm going through the presentation. I saw the TWAs that Bill was flying, and I was amazed by how they worked. At that time, I was really interested in team racing, and I spent the time there timing team racing with the other guys. Now, I saw that the TWA fly, and then Bill was amazing because he did a presentation during the championships where he explained how they developed the TWA and how the tune pipe worked. And that's really what got me hooked on the idea, because I was enthralled by how these pipes worked. And that set me going. I mean, I was just a little lad. Unfortunately, I didn't actually get to meet Bill at the time. That was a long time later before I did. 2004, I eventually met my hero, and I was able to tell him that he'd started me on my life's work, really. And without his flying the TWA in the presentation, I don't know what my life would have been, but it would not have been designing and building model airplane engines. As far as two-stroke development went, there was a huge amount of work after the Second World War in East Germany. Walter Carden, who was working for MZ, was doing lots of development along with Daniel Zimmerman, a lot of small two-strokes, 125cc's and then 50cc engines. And they had this leap forward when Walter worked out how to make the resonant exhaust systems work. And that was one leap forward from him. That was coupled with the Zimmermann valve from Daniel Zimmermann, and the engineer at MZ, who was also the rider, Ernst Degner. And they put their technologies and their brains together, and they produced some amazing engines which began to show the world how quick they could get 2 strokes to go. Then a big breakthrough for most of us, the rest of the world, was 1961. Ernst Degner defected while he was a race in Japan. He defected to Suzuki. A lot of you will probably know the story of how he vanished off the track and in Sweden and turned up in Japan. And his family were spirited away out of East Germany by one of his friends. So it was a real cloak and dagger operation to get him out. The real sort of well, not the secrets behind, but the thing that caused the extra development was how they managed to run a double bypass system with a boost port instead of the old-fashioned single bypass scavenging, which had been in use prior to that. And by doing that, they could get rid of the baffle on the piston, make a much more efficient engine. And by 1964, these technologies have started to move into model aircraft engines. Bill Wisniewski from K&B, which is a Japanese engineer with Ernst Degner working on one of the engines. And then in 64, Bill came to the champs with the K&B 15, which became known as the Wart for obvious reasons because of all the lumps on the side of the crankcase. This engine had through piston porting rather than channels up the outside of the crankcase, and was that leap forward in performance that allowed him to, well, he couldn't use nitro because the rules had changed, but the performance came because the scavenging was so much better. And the port layout was similar to that used by MZ, which I think we have there. That's the basic sort of port layout which was in use, MZ use, and Bill pretty much followed that. So you've got the 2 bypasses and a single boost port, which assists with the scavenging. The principle of the operation of this is that with the 2 bypass ports, the gases are directed forwards on the cylinder, and then the 3rd port, which is up at a different angle, causes those gases as they flow into the cylinder to go up the cylinder wall. And I apologize, there's not a better drawing here, but they go up the cylinder wall and then they go over the top of the cylinder, over the top of the head combustion chamber. So you get an even flow of gases going through the engine, which obviously improves the way they're all going to go. Back to that. My slides are not quite in the order which I had them when I looked at it earlier today. Right, now moving on a bit to when I'd started with Ron in 1977. Now, the first engines that Ron produced were based upon this, the K&B 40S. His prototypes used the K&B cylinder, piston ring and conrod, but they were front induction, obviously for RC use. And I got there in 77. They'd already started some of the production. I finished it off. I built 1,000 engines and ran every single one of them before they went for sale to make sure the ring was bedded in correctly. Unlike the 40S, which had an iron cylinder, and that bedded in quite quickly onto the ring, Ron had decided we were going to use steel, nitrided steel, which in theory was a much better cylinder, much harder surface. But the problem with that was that it took ages for the ring to bed into the cylinder. We did actually find one interesting issue with the Dykes ring with the hard cylinder, that after it had run for a while, the top of the cylinder had a dent where the ring was at top dead center, and combustion occurred and the ring expanded. It dented, it worked through the nitriding, and the ring would actually catch at the top of the bore into this groove. So subsequently we changed to a cast iron liner which made life from production a lot easier, and eliminated this problem of the ring cutting into the top of the cylinder. The first Irvine 40, this is the crankcase. We had a much on the Mark I, it had a skinny old front end. We only ran that for about a year because we realized that the front end was just too skinny. So we introduced this as the Mark II with the stronger front plate. The 40S, which had been designed initially for rat racing and for pylon racing, hence the disc valve arrangement, was aimed to run at quite a high RPM. And the fact that the initial Irvines followed the port timing was great in one way, but it further down the line, it revealed some issues which we had to correct as we developed what we were going to do. As far as speed flying is concerned, which is, of course, is my big interest, and I've been doing that since 1969. Ron, when I got to start with Ron, he gave me carte blanche. He said, you can spend as much time as you want, lunchtime and in evenings, working on making your own 15 engines, which I was very thankful for. Used all the machinery at work and was able to do that. Now, by 77, of course, that the Rossi 15 was the engine to beat in F2A, and of course I started to use them. And once I got with Ron, I was able to learn a lot of work how the Rossis worked, and eventually I started making all my internals for the engines, different crankshafts, bigger crankshafts, made piston cylinders. Eventually we made our own cylinder heads, which thanks to Charlie Taylor we were able to do with the head, which in fact we're still using now on the current engines, the same basic design of head. I also acquired at that stage a couple of Bibles. One was the Gordon Blair's The Basic Design of Two-Stroke Engines. And this book is still available, along with the later version, which is design and simulation of two-stroke engines. Now, they are phenomenally expensive. The original version is actually cheaper now than the later one, but they are amazing books. There's so much information in there. Okay, a lot of it is perhaps not relevant to what we're doing for our model airplane engines, but if you've got the time and you can get hold of a copy, it's great to read them and go through them all. Now John Bristow had been a good friend of Ron's, and in fact, John's business started, or Ron helped John's business to start with the deluxe materials. And at that time, John was working for Castrol in the racing division. And so was able to get hold of lots of SAE papers, which he brought across for me to peruse. One of which was a paper produced by Nato and Nomura from Yamaha about specific time area coefficients. Now, these are a light bulb moment, because once you start to understand those coefficients, you know where you're going with designing the size of your ports. Up until then, it's sort of a cut and try, see what other people are doing, but you can't make your own ideas of what your design would be without this information. And it was, as I say, it was a light bulb moment when I was able to do that. I also studied some books by P.E. Irving, which is on the modification of the two strokes, Alexander Graham Bell. Another extremely useful volume was one by Gordon Jennings, and it's a two-stroke tuner's handbook, which you can probably see. This is it. Now, if you can get hold of a copy of that, there's an awful lot of stuff in this Jennings book, which is extracted from Blair's work, and it's put in a more simplified fashion. And he writes very interestingly the way he writes his book. And I found that extremely useful as a reference book for me. So where does all this take us when we're, excuse me while I put some slides down, is your Rossi, a bit about pipes, that where does that go when you've got all this information? Now, armed with this knowledge that of how to make engines go quickly, because by this time I was making modified cylinders for the Rosses and working out how that would go at that stage, at about 38,000 RPM engines, that I've realized we could apply that to everything. And it's just a matter of taking your specific time area coefficients and applying them to a different end of how the two strokes were going. And we realized at Irvine Engines that it was absolutely essential to make engines that were less noisy to keep flying fields, because then, as now, noise is a big problem for RC models. So we decided the only way to do this was to reduce the RPM. Now, when we came to do the Q40, which was the first engines which we produced to reduce noise, it coincided fortuitously with the arrival of APC propellers, which, as you know, are pretty efficient, and they're fairly quiet in themselves. They have the tip shape is very good for reducing that beat off the end of the blades. But we modified the timings from the original 40 in order to get a better flow through the ports. I reduced the bore from the original Irvine 40. So we ended up with a thicker cylinder wall, which gave us a better flow direction for the gas as it came from the crankcase into the chamber. We also timed it so it would peak at about 15,000 instead of 20,000 RPM, which so many engines at the time were doing. At 20K, you got huge horsepower, but useless when you come to fly. You had to fly on a 10.6 on a 40, which was in itself was going to be noisy. And that put the engine RPM at that irritating RPM that really caused the annoyance to everybody. So the idea behind the 40 was to reduce the RPM, which would do two things. A, it would make it quieter because the prop wasn't so quick, and also it took away just below that awful, that annoying RPM and annoying noise level that you had previously. So I did an experiment, which was a bit crazy. So I made an engine with 110 degrees of exhaust and 100 degrees of transfer, cut down the induction duration to about 180 degrees. And then the muffler I used, and those of you who've flown pylon racing recognize the 20 size super silencer, that went on the end of about 20 inches of 5/8 diameter pipe. The performance of this was quite amazing. On 11.7 propeller, it would fly anything. It was, once it was in the air, you really couldn't hear the engine. Now, we hummed and hawed about whether we should go production along that line, but concluded that getting that great long muffler was going to be a problem for operational use, and it was okay to prove a point, but it wasn't going to be viable as a production engine. So we moved on to the Q40 as it was known, with the reduced exhaust time. We came down to 140 on the exhaust and 120 on the transfers and 112 on the boost. Then that coupled with the Q40 silencer, which you can see here, and this I've cut away the outside so you can see how it would come. The gas is coming in at this end. They come out through all these holes, end up going down the very narrow gap between the two cylinders, and then out through here in the exhaust. We actually had an additional part in the exhaust which had a cross hole here, so the gases had to come out, turn right, come here, turn right again. So each time you turn the gases, they lose a little bit of the noise volume, and then it was out the back. And by making this fitted into the standard Irvine 40 casting, we ended up with a bigger volume, and this self-insulating exhaust thing, because you had the exhaust gas around the outside of the inner chamber, and it added as a noise attenuator. We ended up with effectively a very quiet engine, and it would also turn 11-inch props instead of 10-inch props, 7-inch pitch instead of 6-inch pitch, and the performance was very satisfying. And still, I get comments about saying that the Q40 is probably the best one you ever made. No, I won't necessarily disagree with them. Now, when you're taking this knowledge and you want to move to a new design, what do you have to do? Well, firstly, you decide what it's for. Is it going to be RC, fixed wing, RC helicopters, cars, pylon racing, control line speed? Then you decide what exhaust system you're going to use. Is it going to be an expansion chamber, a simple muffler like we have here on the Q40, or are you going to use a resonant exhaust system? Because this choice is initially basically to decide how much BMAP you're going to generate. And when your BMAP, you know that for your basic design calculations, it's one of the things you need to know. And it's generally speaking, within a muffler, an ordinary muffler, you get about 6 bar, between 5 and 6 bar you can get as a BMEP. With a resonant exhaust, you can get up to 15 with the most powerful engines. And of course, you have to define the RPM that you want to peak at. Once you've got all this information, then if you have it, which I did by this stage, I had the Blair book, and with it came a number of programs. These are all DOS programs. Otherwise, I could show you one running tonight, but I tried to run it on my Windows 10 machine, but without a special emulator, you can't do it. So I did some runs today on an old DOS machine, which I was able to take some photographs and give you some pictures of what it would do. So what we have next slide here is the program 3.4 from the Blair book, which gives you the port layouts or the port sizes you're going to need in order to fit the parameters you want to run the engine at. So you put in, we're using these, right, it's slightly awkward the way you put it, we have to, is a DOS program. And so it's not like we're so used to today of put numbers into boxes. So you put your basic information of your engine in, which is your bore size, the liner thickness, what exhaust port you're going to start with. You decide on what you're going to have as your targets for each of the port angles to come in here. The size of your boost port, the angle of the boost port, the angle of the transfers come in. Now you'll see on these engines that the UPM, which is the degree angle of the transfer ports, I got that at 0. Well, that was forced upon us really because one of the things you have to do when you're producing engines for mass production, you've got to design the engine to be able to make it on the machinery you've got. And we were making these parts on a mill turn machine, but we only had one cutter, which was an angle. That was for the boost port at 45 degrees. So it meant we had to run the transfers in at 0 degrees to save a second difficult hand operation to put an angle on the top of the transfer ports. And because we had to have this 0 degrees on the top of the transfer ports, we have to make serious changes on what angles these two go in compared to, if you look at an OS, you'll find that this rear angle is pretty much similar, but the front angle will probably be 65 degrees, not 82 degrees, because they're angling their transfers up at anywhere between 12 and 15 degrees. And also they're running the boost ports, some at 60 degrees, some at 55 degrees. And again, this is possible because they have a 5-axis machine for doing the cylinders. So we had to tailor the design to what we could actually operate. So you run this and you end up with some information, really useful information, which is, it tells you the port width of your main transfers, which comes at 13.6, and that's measured from this face here to this point here, because it's the perpendicular line at which the gas comes in. And it also gives you what the totally effective port width is. So it's taking this, all the ports together, telling you what the total effective width is. And it's calculating that by using the angle here, because as you increase the angle on a port, you reduce its effective area. And then you get the numbers, it gives you the effective area in there. We then go and look at this page, which is on the Blair sheets, is page numbers, or is program number 61. And program number 61 gives you the numbers for STA. The mouse has moved over. It calculates for you, with the information you've given it, what STA you will require in order to get the performance you want. So we've got the exhaust area is 0114, and the transfers, you've got a target of 0065 to 010. Oops. Now we transfer that, we relate that over to an Excel spreadsheet, which hopefully will come across and come up on your screen. There it is. Now, of course, I've got a bar at the top, which is really in the way. A bit smaller. Okay. So the first page we'll look at on the spreadsheet is my one labeled STA, where I've got in the figure, which comes off the program 61, and the two transfers of 065 to 1. Well, I went for somewhere in the middle, 085, and that comes and gives me here exhaust is 7.2, and it needs to be 5.82 millimeters high, and the transfer is 13.65, needs to be 3.5 millimeters high. So we can go back to spec 1, and in spec 1, that's where everything, all the design parameters for the engine go in: bore, stroke, liner OD, connecting rod length, all these parameters which are necessary to be able to calculate things. And then we end up with 582. That gives us 145 degrees of exhaust, 3.5, 112 degrees of transfer. And we found that the engine works better by reducing the boost timing to be 4 degrees behind the transfer timing. I think that's a function of the angle of the boost port, which 45 degrees. It works better when it's got that lag behind. So that ends up 108 degrees on the transfer. And then the next sheet here is the first prototypes, which we build, we measure it, put in the numbers and see what figures we actually got, which were pretty close on that first one. The next page on this workbook is this one here. And taking the information which we've just put into the system, it tells me, and this is all to help with the drawing of the engines, laying up of the engines. It gives me specific numbers for the height of the case overall, and all these numbers here. And that just makes it easier to pick up and draw. You don't have to get a pencil and paper out. It pops out of this little workbook. Similarly for the ports, picks up the numbers for all the ports, and then for the cylinder, it gives all the heights for the cylinders all the way down the numbers, so it just makes all the drawing that much more straightforward. Right. Oh, God. Let's knock my water over. Bear with me a moment. Okay. So having got all that done, and we can then progress to drawing the thing up and making up the prototypes. So, oops. Cylinder head design. Now, again, there's a Blair program which gives you, in fact, there are a number of programs in there. So you can work out your head designs on different shapes of head. Now, preferred shape of head we found for RC engine is what they call the bathtub. Now, it's one you're all very familiar with, that you've got a slightly angled squish band of radius, a little straight another radius, and a flat top. And for throttling and for general working in an RC engine, this seems to be the best layout of the cylinder head. Now, you can see I've got a note here of the trap compression ratio. with the advent of 3D CAD, which is a wonderfully useful thing, so you can measure volumes, or can truly measure that the trap compression ratio of the Irvine 53 was 8.04 to 1. And I did also just a little check on some other engines today, what they were, and the 39 Aero 8.3, 39 Heli 7.41, because that's running at a different RPM, and we'll come to another reason it's slightly different later on. And then the 15R, which is in a piped arrangement, with 705 as the trap compression ratio, but the BMAP is higher because of the pipe. Should go, yes. Now, I mentioned earlier that when I'd started with Ron, he said you can go on and spend some time, you can make F2A engines. And so I decided back in 1978 that I was going to make my own engine. And my first attempt, I made the die. This is all, became the lunchtime and tea break special, that every free moment I had, I was on the Bridgeport or on the Colchester making bits and pieces to produce this. And this is the die in the closed form. And then the open form, you can see all the slides which form the internals of the for the waxes to go into. Because I did this before I had the information from Blair, so I was sort of working a little bit blind, and I had decided that I didn't want to follow the Rossi, just copy the Rossi, that I wanted to have something slightly different. So I followed the port layouts of the KMB 40 and the KMB 21. So it had a split boost port, and the transfers were back at about 55 degrees. So they were sloped further back. You can see that there's quite a space between the boost port and the transfers. But by having two boost ports, it reduces the area on the main bypass ports. Another slide here. The next one shows the internals of the crankcase, and you'll see the inside with the two boost ports. And then this is the internal core, which is a little bit of a jigsaw puzzle. It's quite interesting to make, but there's a bit of handwork to do after you've finished machining it all. Then it all slots together on a central core. And when you come to remove the cores, you pull this central piece out, and then the three other pieces, which you can put screws into, and you collapse them out of the wax. Now this engine it worked okay, but it had some odd characteristics which later on in my work at Irvine's were quite useful in that the characteristics made it would not work properly as a piped engine. In open exhaust, it was fine. But when you were running a piped engine, the transition as it came on the pipe was so rapid that the RPM went up faster than you could increase the fuel flow. So inevitably, it shot up in RPM, and it was then running lean. And I concluded eventually by blanking off these bypass ports that it was due to the fact it had the much wider boost port in relation to the main transfer ports. So it never went past a few prototypes. I did fly one of them, and it was blew a lot of plugs because of this sudden transition of speed. And the importance of this size and angle of the boost ports, which I discovered then, it was emphasized years later when we built the 39. Now, we built the 39 Aero, and that worked beautifully. And then we built the helicopter version, which was okay, idle, flying around at full throttle was great. But when you came to mid-throttle and mid-range, which was important for the hover, the thing just would not run evenly. It was hunting all the time. So after a lot of head scratching, I remembered this issue I'd had with this arrangement of the ports. So in order to fix it, I had to do a hand operation on the cylinders for the 39 heli engine, which was to increase the boost angle from 45 to 60 degrees, and also to raise the boost timing so it matched the transfer timing. So it's an extra 4 degrees of boost timing and the extra angle, and that solved the problem. So that shows the importance of what your boost port does for you. It controls things, not necessarily at the top RPM if it's running on a pipe, because the pipe does all the work, but as the engine goes through different stages at different RPMs, and the shock waves are changing, it just smooths things out, and you can adjust how the engine operates by changing the size and angle of that boost port. So by 1986, I learned a lot more, and along came this, the Irvine 15. The original engines had 12mm shafts and cast pistons. Flew those for a number of years, and then by 93, I'd made a 13mm shaft in the engine, which again boosted the performance. The 94 engine used the basic cylinder and piston for the original engine, which was the CZ121 brass cylinder under a Vanissil piston. And then we produced the Halman specials after that, which all had machined pistons, which are more stable than the cast ones. Now this old engine did quite well. The original engine, we had 3 European champions, 1 world champion, 6 team gold medals, a whole host of things that produced success on it. But by 2009, I wanted to make some changes to this design for quite a while, but at the same time didn't want to make a new investment die to test out the changes. Principally, when I built this, because I'd had some problems with the Mark II Rosses, the crankcases falling apart. I suppose really because I'd put the 12mm shaft and a bigger bearing into it, they fell apart here. I decided to make this a lot stronger, which I did, and it's similar wall thicknesses to the Mark III Rossi and to the Moki, and worked as it worked okay, but it was very heavy, and I wanted to make the thing a little lighter, and I wanted to also to try to change the way the heat transferred out of the engine. So when by 2009, new technologies had come along, 3D printing basically, and I've found a guy who could 3D print waxes for me for investment casting. So the engine, which became the Halman 15R, has a thinner wall section than this, has better cooling because the fins are a more thin area, and the engine is lighter. The lugs are a little bit lighter. I maintain the same bolt positions because really I didn't want to be changing aeroplanes, and I wanted to be able to evaluate between one and the other. So certain things had to stay constant. So we were able to make, there's a wax for the new engine, which was not new anymore because it's 2009 we made these. And that's been really successful. Still holds the world record for F2A, 307.4 kph. And we say we're still popping them today. And as a method of production, I think that's the way. If somebody wants to make an engine now, it's so much easier. Anybody who's got a reasonable machine shop, there are lots of places or lots of people who will make your piston cylinders in Ukraine. But the crankcase, you don't want to make, if you want to make half a dozen engines, you don't want to go to the expense and the trouble of making a die. You don't need to anymore. You produce a 3D drawing, 3D print it, and then investment cast it. You can make 5 engines, 10 engines, whatever. And once you then decide, well, okay, that's all right, or something is wrong, you can simply change the design, print some more, and make a slightly different one. And once you've finalized what you want and you want to go into production, then you can talk about, you can think about going for a die in order to make the engines. That completes all the pretty pictures. And this is the engine with the latest pipe, which is a steel pipe instead of aluminium. Steel pipes we went to because what prompted to do it was English weather, where you would often be out on a day where it might be sunny, but you've got a typical cold wind coming off the North Sea, take off, and as the engine comes on the pipe, it will just blub out because the pipe suddenly cools down. So we went to a steel pipe because it maintains a more stable temperature. And Paul and I pretty much use them exclusively now because our whole setups are now built around operating on the steel pipes. I think I've come to the end of my little 45 minutes. Gosh. Barry, we've got some questions come through, have we? You're muted. Barry, you're muted. Yoo-hoo.
Sorry, Peter. Yeah.
That's better.
Mike Kennedy has asked about 4-stroke engines. That wasn't really the purpose of this discussion. It was very much a 2-stroke engine discussion. Did you do any work on 4-strokes at Irvine's? Were you ever thinking about 4-strokes?
Yes, we did. We did a couple of interesting things. I made a 10cc 4-stroke, which was based upon I used the valve train off the original OS 60 4-stroke. What they called it, but anyway, that's what I used, and I built a 60 engine and concluded that the equipment we had, the machinery we had, we would have to make quite a big investment in new machinery in order to make the parts we needed for a 4-stroke, because it's quite different. But it's the head and the cam systems which are so different, and you do need some specialized machines in order to do that. And we couldn't really make the investment to go in making 4-strokes.
No.
The other one we had a play with, that was really interesting, was a sleeve valve engine. And a chap, I can't remember his name, had come to Ron and said, I've designed this sleeve valve and I've made a prototype. Do you want to have a go at producing it? So I got a call to the office, and Ron gave me this. I think it's a huge lump of metal that the guy put it in. And I took it and I ran it, and the original engine had a cast iron sleeve. Now, if as you know, with a sleeve valve, the sleeve is moving up and down and round and round, which was fine if you've got multiples because you can balance the things. But with a single, with this iron sleeve going up and down, there was no way you could balance it. So that was my first experiments with plating aluminium. We made aluminium sleeve, plate the inside, plate the outside, and it ran. It sort of worked quite well, but it suffered the same as all sleeve valves do. That unless you've got lots of oil going around, you don't get a good seal between the sleeve and the crankcase, and so we decided it was an interesting thing, but we really wouldn't go forwards with it. So that was our dabbling into 4-strokes.
Yeah, we've got a question from Neil Lickford, who's in New Zealand.
Neil?
I think he's asking about that little ear on the transfer port, which is near. You had one picture where you had a kind of it was in the Blair diagrams.
That one?
No, there was a side view of the cylinders. Oh, where is that one gone?
Was it in this?
Yeah. So if you can imagine the two transfer ports,
Yes.
in the diagram, it had a little ears dropping down from it, a bit like a lot of the Italian car engines had. Those.
Oh, right. Yes. The little notch. Oh, I've got a picture. Oh, there. Picture of the cylinder. You might just see it here.
Yes.
Certainly, running up and down little nick. Well, yes. It's a bit of
Neil's question was, what is the side cutout on the exhaust side of the side transfer port?
That little bit there, that cutout. Well, I could give you a technical reason to how it improves the gas flow, but in reality, initially I did it because when you machine your transfer ports, they're offset by whatever, and it might be 6mm, 8mm, whatever it is. So then when you rotate your cutter, your component, and you move your cutter around, you get your nice shape. But if you want to put an angle on the bottom of the port, and you've only got one tool that you can offset, you then have to come in and put that angle on with the tool that's on centerline. So as you rotate the cylinder towards the boost port, it's fine because you get as far as the boost port and it stops. When you bring it back round towards the exhaust port, you end up with a little lip. So to get rid of the little lip, we then go in with a ball nose cutter and machine it off and put a nice little slot.
Okay. Another production sort of question as well from Dylan Roberts. When did the ABC and fancy piston alloys first run in your 15? So I think he's talking about the high silicon, Vanicil, which is what you guys used quite a bit. And what is the typical bore taper on a 15?
Bore taper is 2.5 thou per inch. And what was the question about the pistons?
When did you first start using ABC in your 15s?
ABCs, all the 15s were ABC from day one. We started doing ABC on the Irvine range in 1980. Must be 1980 when we moved to the new facility and had our first mill turn machine. We were able to make ABCs.
Yeah. Question here from Michael Campbell. I don't know the answer, but I'm going to let you. Is it true that you made parts for Formula One car engines for Williams?
We used to make parts for Ilmor.
Yes. You made compressor parts for Ilmor, didn't you?
Yeah. We made parts for Ilmor for something like 10 years.
Yeah. Also, PAW, they made very similar parts for the Judd engines as well.
Yes. Yeah.
Hugh Simmons, I think he's from Australia, isn't he?
Yeah.
Can you explain why the porting layouts are so extreme in RC cars compared to F2A? So, F2A engines got a simple sort of porting arrangement, whereas car engines, Italian car engines, have these complex transfer port arrangements.
Right, but that's something which, when as I said early on in the when you come to design it, you have to decide what you want to use it for. Now, with a control line speed engine, it's going to run flat out for about 15 seconds. Even RC pylon is going to run for a minute, 2 minutes flat out. Model car engines, they run half an hour or an hour in their races. So the heat build-up inside is quite different. And of course, they're running nitro, they're running maybe 25 nitro as well, which changes things. And their whole heat dissipation is up through the cylinder head. So you've got some issues with the pistons. And what all those, or a lot of those ports they have in the car engines, I think help to cool the piston. Because if you can imagine the thing running at the RPM it is, it's got to go for an hour without destroying itself. And by making all those extra little slots, you can get the gases going across the piston and cooling the piston down while it's going. And the other thing they do with some of them, of course, is that with a car engine, you're not actually so worried about the peak power, peak RPM, as typically on a car, it might hold full speed for 1 or 2 seconds on a lap. And most of the time, it's throttling up from through the mid-range or the lower range to get around the corner, accelerating out of corners. So by changing all these little angles on the transfers, you can improve that mid-range transition. I think that's what they're trying to do.
Car engines, it's all about drivability and
and
traction out of the corners. Peter Oliver asked, have there been any areas in improving two-stroke performance that you have wanted to explore, but time and or cost or potential production issues have precluded? So did costs and complications much stand in your way at Irvine's?
Not really. The only limitation was on what machinery we had, that we had to design the engines so we could make them. So as I said earlier, which is why the top of the transfer angles is at 90 degrees to the bore instead of up at 15 degrees or even 20 degrees. And so that was a limitation. But other than that, we could do basically what we wanted with the design, provided we could make it, and that's basically what we did. There are other things which can be done now, which we couldn't do when we were in production. And one is, it's much easier now because you've got 3D CAD. It's much easier to design things so you can get a much better balance on the crankshaft. That you could do a lot of maths and work out how to balance the crankshaft, or you could spend a lot of time cutting and grinding to move the balance weight on the crank web round. And if you look at engines now, the later OS engines, you'll find that all the crank webs they don't cut symmetric either side of the pin. That the side where the window is cut higher than the other side, so you're balancing the crank better. And with a 3D CAD system, you can do that. And if you look at the crank on the later engines, the Halman Specials and things, which are all drawn up on a 3D CAD, they're balanced in that way.
Yeah, good.
So that's an improvement which you have now. The other thing which you can do now, which wasn't available, but it is expensive, is to DLC coat everything that moves.
Yeah.
They do that on OS car engines, and I'm sure that Nova Rossi do as well. I think they ought to do the wrist bit as well as
Nova Rossi in the past tense.
Yes, sadly.
Yeah, it was a big shame. We've got another question from Neil, and it'll probably roll into a question from Trevor Tennant. Have you tried the RSA?
You keep breaking up, Barry.
Have you tried the RSA 444 piston material? So that's the Dutch piston material versus, I think you used Vanicil a long time ago, didn't you?
Yeah, we used Vanicil initially, and then I went to and I found actually it's Brian Turner put me onto a company called Osprey, and they were based down in South Wales, I think it was. Went had a visit down there, and they had developed a system where you could you take aluminium powder, and by spray deposition in a vacuum, they could produce an ingot of materials with high silicons in. And unfortunately, nobody in the UK bought the production for this. And there's a company in Germany called PIAC, who they bought the rights to use it. And I had material from them, which I used the 250 alloy, which is 22% silicon, bits of iron and all the rest of it in it. I used that very successfully. I've also used the RSA. The 444 is good. It's very hard. Although it's very hard, I do find that the wrist pin holes in the piston wear relatively quickly compared to the S250 alloy from PIAC.
Okay. Trevor Tennant asked, Peter, do you prefer ABC to AAC piston liners, and why? So ABC versus AAC.
From a purely practical point of view, ABC is hugely easier to use, easier to produce, because plating aluminium is a real pain. From a control line speed engine, or from a general RC engine uses, a brass is better because it's less expensive. Therefore, your end product for your RC engine is a better price. For a speed engine, aluminium, I have tried it. The problem I had with that was the engine was overcooling. That because the aluminium is transmitting the heat through the crankcase quicker than the brass one is, the engine cools down when you fly. So you have to blank off all the cooling. And I'm pretty sure Per Starneston has managed to fly AAC, and he has the whole engine covered up. Even the head is covered. All that sticks out is the end of the glow plug. He's made it work that way. But it seemed to me an unnecessary expense and difficulty, because there's no increment in performance. So you don't go any quicker, but they just cool better, which is why for F2C engines, they're using AAC with integral fins into the cylinder, because they're running for a lengthy period of time with not much oil. They need good cooling, and AAC is better for them.
Okay. Peter, I'm going to have to drop out. I've got to go talk with the AMA about competition in Muncie. Really appreciate it from my side, and there's a lot of unanswered questions. I think we're going to have to call you back. They're quite manufacturing type questions, actually.
Okay. Well, if you let me have the questions, I'll try and answer them, and then we'll, depending on what they are, whether I can develop a new presentation which specifically answers the questions which people have asked.
Andy, can you just capture the chat and the questions and answers?
Yeah, they're all captured automatically anyway. What we could do, we could have a session specifically for question and answer session. Start straight with question. Anybody who's got any question about, perhaps if we could get, obviously we've got Peter, perhaps Neil Tidy possibly along, who knows a little bit about four-stroke engines, doesn't he? We could have an engine panel. Yeah, that would be great. If you could bear that, Peter, you wouldn't have to do any preparation. You just
although it would be helpful if the questions were in advance, because if there's something I've got to look up, or find, then it would be good to be able to do that prior.
Yeah, we could do that, build it in as part of the registration process, so we can get questions in advance, no problem.
Yeah, that'd be excellent.
I'm going to have to go. Peter, thank you very much.
Right, thanks, Barry. We'll have a good meeting with the AMA, and I hope you've everything ready for the champs.
Yeah, cheers. Bye-bye.
See you, Barry.
Bye-bye.
Right. Well, it's entirely up to you, Peter. We can carry on for a short while, or there's 15 unanswered questions. So I think we need to set up a question and answer evening.
Because I wouldn't get through 15. My throat's pretty parched, having been talking for an hour now. So I think I need a bit of a rest.
Yeah, I think what we'll do there is